We get to go inside the machine. We will not be editing that section out.
This is an actual friction stir welder.
It's like the largest fixture plate I've ever seen.
So we ended up building our own machine from scratch.
That's not possible. That's crazy. It's titanium. Mm-hmm. Hi folks, we are here at Fabrisonic with
Justin Winning.
Want to show us around?
I would love to.
This is really, really cool, folks. What's even cooler is we're only in Columbus, Ohio. It wasn't even that far away. And it kind of blows your mind when you realize this kind of stuff is happening. We're effectively on the campus of Ohio State.
We are on the campus of Ohio State, and we're actually sharing a building with the Ohio State Welding Engineering Department.
So we're going to tour Justin's world and see some really cool stuff, but stick around in the video because later on we're going to show off their pretty state-of-the-art additive manufacturing stuff. So your 3D printers, but focus on the metal side, as well as friction stir welding. Also pretty crazy and one of the largest machines I've ever gotten to see or walk into.
One of?
Ed is challenging me. Is this the biggest machine I've ever walked into? It was not, because when we had the chance to tour scaled composites, we got to go into a, like, I don't even want to know, 60 feet or 60 meter. I mean, that was gargantuan.
Here we are with the coolest kind of additive manufacturing, and I mean that in a temperature sense, but also in a cool sense. Additive manufacturing is a different type of 3D metal printing. We're actually building to net shape using ultrasonic metal welding, and then we're using CNC machining to achieve final contouring and profiles.
In the same machine, though.
In the same machine.
Yes.
Seamlessly transitioning between the two. So what is ultrasonic additive manufacturing? It's a friction welding process where we're using high shear rate forces to scrub metals together to weld down thin metal foils. So here in this machine, we're actually starting with 1 inch wide by about 6 thou thick metal foils.
So it's just like you see like on a stamping machine, there's a coil right up there, huh?
Exactly.
There we go.
So we're starting with these thin metal foils.
Okay.
And then we have our welding device here that actually takes these thin metal foils and welds them down to a substrate.
That's amazing. So in this case, mixed metals.
In this case, mixed metals. Yeah, bread and butter are really copper and aluminum, but ultrasonic additive manufacturing is unique in that it can combine dissimilar metals in a lot of different combinations. It just takes a little bit of development.
Yeah.
So kind of getting back to why is this the coolest kind of additive manufacturing is because UAM, or ultrasonic additive manufacturing, is a solid state process from a joining perspective. It means while we're actually welding this metal down, it's not getting heated or melting whatsoever. So
yeah, so I think of traditional welding, I think of a puddle, which is going to destroy
their properties.
A lot of heat. Yeah, exactly.
Yeah, so here with a solid state process, kind of what your properties are going in is what you get coming back out.
Okay.
With a slight degradation. But here inside of this machine, we're actually using an ultrasonic sonotrode, which is tuned to 20 kilohertz, with 2 ultrasonic transducers that force this sonotrode to vibrate and oscillate back and forth at 20,000 times per second. Yeah, so what will happen is this welding device will actually roll on top of our metal foil, and as it's rolling across and pushing with a slight downforce, it's actually scrubbing the metal against the substrate and effectively welding it down in a friction welding process. And once we have significant or a proper amount of material built up, then we can transition back over to CNC machining.
Subtractive. Get back to my side of the world.
It's a hybrid process.
Right,
yeah,
no,
exactly.
it really is though. It's amazing.
So
this part right here, is this sort of shaft, if you will, is what we see contacting with that strip right in there on that head.
So the 3 main processes or applications that we're doing with UAM is kind of heat exchangers, embedded electronics, and dissimilar metal combinations. Because we're doing CNC machining to get to final geometry, every feature inside of our parts that we're manufacturing actually have a CNC machined accuracy, as well as a surface finish, which when you really look into different types of additive manufacturing out there, there's normally a lot of post-processing that'll go on with them, especially when you consider like a powderbed technology or directed energy deposition
By post-process, you mean like sintering or heat treating, grinding, polishing?
Sintering, removing from the substrates.
Yeah.
There's a lot of post-processes that go onto it in order to get its full mechanical properties and its final finish. Otherwise, it would come out almost looking like sandpaper in a lot of applications.
Sure.
Here, when our part comes off of the machine, this is exactly how it looks without post-processing whatsoever. So this is actually a heat exchanger demo sample replica of a heat exchanger on the Mars 2020 rover.
Oh
So,
my god, this is amazing. So this is a continuous coolant loop line.
Exactly, right.
And that's made in process one setup, one operation.
It
Well,
is.
actually, if you
I guess there's two ops.
two ops sort of, but yeah, all of that work for there is done in one.
Two setups, but almost all of it's done in one
Yeah,
setup.
it's amazing. So how was, you said this is a prototype, is this how the Mars rover is going to be made, or are they still doing this in a different way?
Unfortunately, the qualification for something like that is set many years in advance.
Yeah, right.
And in 2019, we don't exactly have the time for the
Sure.
qualifications to be met. However, we have done significant work with NASA JPL,
Okay,
where we have gone through qualification processes on our components.
okay,
So from a qualification standpoint, we're talking kind of CT scanning of the part to make sure that it's completely void-free
okay.
and geometrically hits the tolerance exactly what we were supposed to hit. It's got a burst pressure above a certain threshold. So in our circumstance, it's about 3,000 PSI. which
That
means
aluminum,
This aluminum wall, this 35 thou aluminum wall can maintain that over 3,000 PSI burst pressure.
serious?
Exactly.
gosh, that's
yes.
amazing.
And it also has hermeticity, which, when you're considering the process is nothing but continuous welds, there's a lot of opportunity for there to be discontinuities that would be a leak path.
Okay,
And when you're putting something into space and you have no ability to fix the leak, it has to be
Got it.
perfectly sealed.
it's a heat sink, what I think of it.
It is, yeah. So the electronics on the Mars rover, or really any satellite or something going into space, or even the electronics in an airplane for that matter, I mean, you kind of have to keep them at a certain regulated temperature
Yep.
in order for them to perform optimally.
Okay,
So kind of what we're doing is we're kind of building the chassis to which those would be mounted, or
Yep.
the structure to which it would be mounted, and integrate the cooling into the feature. So it's something you couldn't traditionally manufacture. So the current manufacturing method for a panel like this would really be just bolting and epoxying a bent tube onto a plate,
Right.
which, when you think about it, you have lots of moving pieces,
yeah,
much more complicated, a lot of opportunities for failure,
yeah.
as well as the weight savings.
I'm thinking back to like when I was a kid and I would, try to hack overclock computer chips by you put your thermal paste on there and a bigger heat sink. And
Exactly.
I got to think that
So-
this being monolithic is a better transfer of
Exactly.
heat.
So if you look at just the sheer thermal conductivity increase,
Yeah.
when you get rid of the epoxy and you have different wall combinations, by going to monolithic 6061 aluminum in the T6 condition, we're able to get good mechanical properties and good thermal properties with massive weight savings.
Yeah.
By getting rid of that epoxy and all the other pieces, we achieved a 30% weight reduction compared to the current manufacturing method, in a significantly shorter lead time.
Got it.
So this part, just as an example, kind
cool.
of start to finish, was under 2 weeks.
Got it.
So
Not to print and make this, but the whole design
the whole
process.
thing.
Yeah, exactly.
I mean,
got it.
yeah, once we had the design finalized, the programming from
Yeah.
a CNC standpoint in Fusion,
Yeah.
and actually manufacturing it, start to finish, was about 2
Yeah,
weeks.
it's not that big a deal. And this is normal aluminum. There's nothing special.
That is normal aluminum.
Yeah, it's
I mean, that's
amazing.
pretty much what you're buying billet from
Yeah.
your normal supplier.
Got it. That's cool.
So a couple of other examples. We also have, this is a heat exchanger for a small satellite.
Okay.
Similarly, by printing the tube into the part, you have a performance increase because that fluid is that much closer to all the meat around it that's absorbing the heat or reflecting the heat, one of
Yep.
the two.
It's beautiful too. There's something like very eye-catching about
Yeah.
seeing it as integral.
And there's no post-processing on this at all. This is how it's coming off of the machine, and it's a great removing all the other steps that you occasionally have in other additive processes. We're also working on developing an antenna structure. So this is actually a sub-specimen of an antenna. Weight is of such an importance that we needed to find some way to pull it out of a 35 thou wall piece.
Okay.
So when you think of a 35 thou wall, it's already pretty thin. So the engineers at NASA thought, what if we tapered it from its actual link point all the way to the far point to
Okay.
reduce the weight where it doesn't need to be?
Sure.
So what we're actually developing here is
But that's tapered, so that can't be an extrusion because of the taper.
exactly.
Oh my god.
So it couldn't just be a bent pipe.
yeah, right.
So, and it's tapered on the internal geometry, and you couldn't really CNC machine this. But if you took a bent pipe and tried to CNC machine it, I have a feeling you'd have a hard time hitting a 20 thou wall.
Yes. Wow.
So here we're actually going from a
Yeah, so
40
you can
thou
literally,
wall.
you can literally see the thicker wall here, and then so this tapers over a shorter distance. Then it tapers out to the 20.
Yeah,
thou
it
here.
tapers down to 20 thou.
It's amazing.
It's very, very small. It's an interesting challenge. that's for sure.
Yeah.
But it's something that you really wouldn't find yourself making with any other additive manufacturing process.
Okay. This is so cool. We were shooting this before we started filming, and this is a way of, you called it a shunt?
Yes,
But
it's a thermal shunt.
Yeah, so it connects at each end, and it's able to, with these, you said these are almost as pure aluminum as you can purchase.
Yeah.
And it's able to pull heat from one side to the other, but also offer that flex. And it's just like, this is so cool. Justin can probably explain that a lot better than I just did. Sorry.
No, that was great. But it's just for space applications where you're looking for transferring heat or cold from one area to another, and having that flexibility to be able to withstand and not have any forces or stresses build up during the launch.
During the launch, that's so funny.
Yeah,
right.
so during the launch, one piece over here could be moving all over the place, and the other piece could be stationary, and you wouldn't have any broken connection or any unnecessary stress.
Sure.
We also get into embedded electronics. This welding process, when we're welding coppers and aluminum alloys, the max temperature that our metal actually sees is really only about 200 Fahrenheit.
Okay.
So if you think 200 Fahrenheit, I mean...
Not even boiling water.
Yeah, not even boiling water. And that's only for a few milliseconds. So,
a few milliseconds.
So it's such a short period of time that it has even less effect on whatever you're building into the part.
Okay.
We can embed just about anything as long as it can handle the ultrasonic vibration and the downforce required. So one thing that we're commonly finding is we're embedding fiber-optic cables for both data transmission as well as strain sensing.
Okay.
So
inside
the part. So kind of getting back to that concept of Internet of Things, kind of connecting what you're making to the system to be able to get feedback from your parts. We can embed fiber optic cables to be able to get pressure readings, temperature readings, and strain readings inside of the part.
Along the cable, from the cable.
All the way along this cable.
It's amazing.
Versus what a lot of people might know is just like a surface mount strain gauge where you're only getting one instantaneous point.
Okay.
By using a fiber optic brag grating, we can get continuous strain measurements along the entire length. So you could embed a meter or so of fiber inside of a part and measure the strain very uniformly across that entire length inside of a part.
So it's literally almost like you're able to cast this inside the middle of a part. But
exactly. So for an example being, if you had an aerospace wing spar that you wanted to measure the life of it and make sure or detect cracks along it, what we could actually do is it's been broken off. But these are the fiber optic brag gratings that come in and wrap around inside of this part. And that allows us to measure the stress at any point along here. So if in service this had been fatigued to the point of cracking, we could use the interrogation of that fiber to pinpoint exactly where the crack is, and observe it, track it, and much less visual inspection.
So this was made on this machine or a machine like this, where
this was made on this machine.
At some point, somebody has to go physically add this in, and then it resumes.
They would just connect in, which is this part right here. There's a beam bracket that we actually did do that exact concept on. So this has a fiber optic brag grating that is going through around that pinhole, which is a clevis pin. And we actually did lab tests on it to measure the life of the fiber in crack propagation. And it's just amazing the data that you can get out of such a fine sensor. And even when we put it in there, it's so small that it has like no detrimental effect. Normally, if you were to put any other strain sensing device onto a piece, it would be so large that it could affect the life of the part.
Right. Well, and you don't have to take the part out of service to get this real-time data.
Exactly. You just connect onto it. And just as like an example, let's see if this works. So like this is a monolithic block of 6061 aluminum where we actually have fed the fiber through all the way across, kind of seamlessly. If you look around it, there's nothing there, but just both ends.
That's so cool.
So you have continuous transmission of the light all the way through. So this would be like a data transmission application. One example that just about everybody will recognize is embedded thermocouples.
Okay.
So just for temperature readings inside of a part. So we've embedded this. This is actually for me sitting my coffee mug on in the morning and tracking my coffee temperature. But we actually have a thermocouple right here underneath our logo. And by putting my hand on here, I should be able to get it to warm back up.
It's really cold right now.
It is. There it goes.
Yeah.
So we're rising. It's a lot of thermal mass right there, but it's rising. And this kind of leads its way to other types of connectors.
It's funny.
So like a USB connector. So truly getting the data straight out of your part. Could be done by having all of your sensors inside of the piece. And this is actually just a foil strain gauge built inside of here. So there are easier ways and different ways of getting data out of your part. And after heat exchangers, embedded electronics, we kind of get back to these dissimilar metals. Because we're not heating them up, we don't have to worry about the bad intermetallics that'll form between two metals when you get them overly hot.
Okay.
So kind of if you looked at like a phase diagram of copper and aluminum, if you were to get them hot in intimate contact with one another, they would form an intermetallic, which would have bad mechanical properties.
Okay. So you can't like friction weld them together like you see.
You could friction weld, but you couldn't arc weld.
Okay.
So if you were to get them very hot, they would form an intermetallic that would be brittle and possibly fail in service.
Okay.
Would fail in service. But here, using a solid state process that is low temperature, we can kind of seamlessly build and transition between those two without any deleterious effects to happen.
It's amazing. And then this can be machined and...
This could be machined to whatever profile. You could just make something fun if you wanted to. But mainly talked about copper and aluminum, but we can also get into dissimilar metals like aluminum and titanium, moly, Invar, Inconel, stainless steel.
So you can get all that
tantalum.
material on these strips.
Exactly. It's actually very easy to get this feedstock. So,
Really?
so
That's
normally
funny.
if you're looking at like a powder bed technology, you're talking hundreds of dollars per kilogram.
Yeah.
Or, it's very expensive.
Yeah.
Relatively very expensive, depending on what the alloy is.
Yeah.
For us, we're normally talking for aluminum a couple of dollars per pound.
Really?
So it's a very
yeah.
cheap feedstock, and it's not dangerous.
Well, that's what I've heard. I've heard that the powder metal machines sometimes require like a explosion-proof room.
That's true.
Okay.
Yeah. In some
This does not
circumstances.
require an explosion. Much
Yeah,
less
because
exciting. No explosion room.
There's no explosions here. We actually open atmosphere. So another factor
Oh, yeah.
to powder bed systems is you have to have them with a shielding gas, because otherwise bad properties will happen to the metal. Whereas right here, if you look at our big machine, the top of it's wide open.
Yeah.
We don't care what the atmosphere is. We don't care what the temperature is. And we don't have to track it because it doesn't affect the properties of our parts.
Affected properties. Got it.
Yeah. So, and one other thing that we can do is embed ceramics and 3D print ceramics for like armor products.
For armor products?
For armor products. Yeah.
Armor,
So
like defense, military
defense.
armor.
Yeah.
Really?
Like I'd like to make a chest plate eventually.
Yes, that'd be amazing. Oh my
Yeah.
God.
So we can actually start with
I don't
very
know if it'll fit in the machine, right? It's going to be difficult when it rolls over you.
maybe. Yeah. But we can actually start with really high strength metal matrix composites.
Okay.
So this is a ceramic that is surrounded by metal.
Okay.
We're actually using aluminum around the metal matrix composite.
Does the ceramic respond to the ultrasonic process? Like, does that actually get...
It's strong enough that it doesn't really care. The aluminum's what's doing the real bonding.
Got it.
That's why it has to be in the metal matrix composite.
I see.
So here we have 220 KSI fibers in a metal matrix that we can 3D print with our machine to selectively stiffen our parts.
Yep.
Or selectively achieve better like fatigue properties, because this is 220 KSI, whereas most aluminums you're normally in the 45 KSI range. So 4 times as strong.
Got it.
And it has temperature insensitive kind of strength. Well, not truly temperature insensitive, but at higher temperatures
Ceramics
it still
have a high
maintains
temp.
its strength.
Got it. That's really cool.
So different combinations, sometimes to make pretty things, sometimes to make really functional things. Here's an example of 3D printing. This is from a larger part, but 3D printing a heat exchanger where certain regions of the heat exchanger were aluminum for strength and mounting, but copper for the fluid paths, so that the fluid would wick out heat much faster.
Better.
So you can get a part that has the thermal performance of a pure copper part, but with the weight savings of having it mostly aluminum. So significant weight savings, which when you're talking about putting heat exchangers on airplanes or something that has to fly all over the place, the weight savings makes a big difference.
That's really cool.
So those are the 3 main benefits. Actually, this is a really cool part. So as far as selective stiffening, so this is a 6061 aluminum plate where we've selectively stiffened the ribs.
Yeah.
So if you look from the end, you can see these tiny little gray dots.
It's like rebar.
It's rebar. It's rebar in the parts. So we can bend it around these curves.
Oh,
and
really?
Selectively, yeah. So it's bent in there, so it truly is like a rebar inside of our parts.
So
for
how did that get
selectives.
laid down then?
So
Are
what
they
we would do,
pre-bent to match?
they're a little bit flexible. So
Okay.
what we're going to do is we'll actually machine in the channel.
Okay.
So we'll just use an undercut end mill or
Yeah.
a ball end mill that matches the diameter of
Sure.
the rebar that we're putting in, and then weld directly over top.
Yeah, that's amazing. It's funny because we've started to hear more about hybrid manufacturing. What does a milling machine have a 3D printing attachment hat, or does a 3D printer have some milling? But this is hybrid in a much different way and kind of cooler.
So
Yeah.
it's a seamless transition, and we have 3 variations here at Fabrisonic, and I can't wait to show you
Yeah,
all of
that's
them.
awesome. I want to see Big Blue.
All right,
You guys had this machine built, you said?
this is a fully custom machine.
Fully custom machine.
So kind of built from the ground
I
up.
need Ed to cover his ears right now because otherwise he's going to inquire about more details about custom building. This is amazing.
Let's kind of watch a very high
Sure.
deposition rate.
Sure.
So here we're going to 3D print aluminum tape. So here what we're seeing is actually 6061 aluminum being printed at 200 inches a minute.
That's moving 200 inches a minute. So what you could do now is you could pause or stop pursuant to your CAM program, and you could machine features in here or change the bands and then continue laying more material down.
Exactly. It's kind of part dependent to figure out when you transition between additive and subtractive.
Okay.
But it's a pretty seamless transition when it actually does come to that.
Obviously, when you order one of these machines, it includes a Gibson SG. You like it?
I like those buckets for the thickened pads.
With the pads?
The thickened pads for it to sit on.
Oh, you
There's buckets
It's like
for
kitty.
full depth.
So
yeah.
someone has a cat, kitty litter. Yeah, Ed and I were talking about this. It looks like it's so you didn't have you can't do a casting necessarily on a one-off machine, but it looks like a bunch of weldments.
Huge weldments.
Huge weldments, yeah.
Crazy.
Wait till we go inside though. The size of the screws, impressive.
So another good feature of this machine worth mentioning is that it actually has 5 axes
Look at
of
this.
welding capability. So here I'm going to drive it up into the air.
Watch this.
We don't actually have a 5-axis part to weld on right now. If you look at the welder, we actually have the ability to roll across complex parts.
Amazing.
This machine in particular actually has a 6 foot by 6 foot by 3 foot work envelope.
6 by 6 by 3.
6 by 6 by 3, yeah, it's a pretty massive work envelope. Now, realistically, you'd never actually want to 3D print a part that large. However, with that kind of capacity, what it allows you to do is to start with a very large part and just add select 3D printed features.
Very good. Wow.
So we could go ahead and put a very large part inside of there and instrument it with some of the sensors that we talked about earlier.
So you could bring in an existing product, vehicle, etc., and you could actually lay down material on. You may have to do some surface prep, but
A slight, cleaning and flattening of the area where you're going to weld, but you
Yep.
could do like repair on a part.
Okay.
Or seamless joining, or add a different metal that you couldn't add any other way.
Okay.
And it can all be done inside of this machine. So one quick piece to note is I keep saying seamlessly transitioning between additive and subtractive. So if
Watch
you actually
this.
watch the weld head up here, whoop,
Rotates out of the way.
yeah, and just like that, we can transition from additive to subtractive.
So it's a little hard to see from here, but right over there is a traditional milling spindle with a, would you say 24 tool changer and HSK 63A spindle?
Exactly, yeah.
It's amazing.
All right. And now you
We get
guys
to
can
go
hop
in.
on in.
We get to go inside the machine. Oh my God. We are inside the machine.
Take a photo of this.
You could have a small party in here.
You could. We've had over 20 people inside of here.
Okay, so the Sonotron
Sonotrode.
is right there.
So this is the real moneymaker right here. That's
Okay.
the welding device that's doing all the hard work of printing
It's
the material.
vibrating left to right at 20,000 times per second.
Exactly.
Okay.
While it's pushing down slightly.
Okay, but the push down happens from the Z-axis system.
Exactly.
Okay.
Yeah, so there's a load cell built into it to control the load.
Okay.
Just one of the process parameters of UAM. So here's where the feedstock rolls underneath our sonotrode.
Yep.
And these transducers are actually taking that sonotrode and making it vibrate and oscillate back and forth at 20,000 times per second. And then we carefully control how much it's moving back and forth.
Okay.
So
Why one on each side? Why can't you have one on the left or right side and the other be a slave or idle?
because we want more power.
Okay, more power. It's the Binford 9000. of
Exactly, it's the
sonotrodes.
Binford 9000.
Got it.
So each one of these is a 4.5 kilowatt transducer.
4.5 kilowatt.
So 4.5 kilowatts of power can be pushed into our sonotrode in order to scrub the metals back and forth.
How do you dump? I'm not an electrician or electrical engineer. How do you push that much power into something that's not really moving? Doesn't that just turn into heat?
Part of it's turned into heat, but it's all just going into the piezoelectric ceramics.
So it is being consumed.
It is being consumed by the
Wow.
motion of the ceramics.
It is,
So
wow.
piezoelectrics are a type of ceramic that when you apply a voltage to them, they expand or contract
Okay.
based on their polarity. So right now, these piezoelectrics are designed to move left and right in this machine to give us our scrubbing motion. So
Yep.
it's applying a 20 kilohertz electrical signal to allow these piezoelectrics to move back and forth at
Got
20 kilohertz.
You certainly hear that word in like microphones, consumer, like guitars, that kind of thing.
Exactly.
It's similar technology, but different. It's just level of
Different level of power.
add a couple zeros.
So
on
we
price
have
and-
with two of them at 4.5, so it's actually 9 kilowatts of power
Okay.
capable of going into our welding device. And typically, you're not seeing actually needing 9 kilowatts
Okay.
of power. That's kind of a very extreme high power. But for printing aluminum like this, we're really
That's
only
amazing.
pulling around 1,500 watts. And I guess I should have had you do this earlier, but if you just go smack your hand on here right now,
Yeah, we just made this.
It's just cold. Yeah,
maybe
we just
3 minutes ago.
Yeah, so it's
Yeah.
chilly.
Yeah.
I mean, this is true solid state, cool
Yeah.
additive manufacturing.
And the texture just comes from the texture that you have. If that were a perfectly mirror polish, it wouldn't be able to impart
Exactly.
the left to right motion.
It has to be able to grip on the
Yeah.
foil so that the foil is able to scrub against the substrate.
Yep, got it.
So
Interesting. I like the word scrubbing. It's a
it-
kind of a cool use of that word.
Yeah, exactly.
Like doing the dishes. And it's cool to see how clean that coil is coming, being fed through.
Yeah. So we start with a lot of pounds of aluminum, and we just throw it down onto a substrate and create the net shape.
Yep. So you guys said you had this machine built just to do, you knew what it was going to do. It was going to be a
Exactly.
milling machine with this.
Exactly.
That's
So
amazing.
we kind of did the fail fast, fail cheap sort of mentality behind this, where we took an old knee mill and we actually tested out the welding capabilities.
Okay.
And then kind of using that as a baseline, we knew what parameters to build this machine
You went
to.
from an email to this.
Exactly. So it was a
Yeah.
little bit of a hop.
I like the way you guys think.
It
Oh my
was
God.
maybe a big hop, but it was kind of a necessary hop for the technology
Mm-hmm.
of ultrasonic additive manufacturing.
You can see the two rails mounted on the weldments there, and then for your Z, and then you've got two more on the Z. So the Z has 4 total on the back side. In fact, do you mind if we walk over through there?
Sure.
I gotta watch. So yeah, literally, there's the actual milling spindle.
Exactly.
There's your tool change arm. Yeah, you can see. Look at the size of the screw. It's amazing. So how much force down are you pushing with?
So typically when we're welding, we're kind of in the 3,000 newtons to 5,000 newtons
Okay.
realm. So just a couple hundred pounds.
Yeah, not that much.
But obviously, when you're overbuilding something, why not build it to go up to tens of thousands of pounds?
Got it.
So this is actually a 10 kilonewton, well, 10,000 pound load cell.
Oh wow.
So it's capable of applying significantly more force than what it normally does.
But the mojo of this welding is the ultrasonics, not the pressure. It's not as if you're pushing it together.
Exactly. The downward force is really just to create efficient scrubbing between your feedstock and the substrate, which in this case is just an aluminum plate.
We did a quick walkthrough before we started filming, and when Justin showed this chuck here, he's laughed because he's like, it's funny. We love the Pearson's the Pearson
gasket.
The
Yeah.
Pearson gasket ring for this. I thought that was
Exactly.
hilarious.
So we have a custom vacuum chuck here that's extremely stiff and works really well for UAM.
Okay.
It's specifically designed to hold two different sizes of plates using the vacuum gasket. So we
Hilarious.
can very quickly transition between different build plates and
Yeah.
different jobs.
It's amazing. Huh. Shear hog. So you got more of these, you said, or different, smaller?
We have different
Different-
sizes
different
of machines.
sizes?
So
Can we go
off to
look?
our side here is our second main 20 kilohertz machine with a very different footprint as well as a different strategy between toggling between additive and subtractive.
It just looks like a vertical machining center. Well, now it doesn't look like a vertical machining center. Huh. Okay, so same thing. Your reel, material reel.
Exactly. So same feedstock, same welding device, same welding power supply. So welding capability, it's the exact same as what the large machine is. The only difference here is kind of the footprint. So on that one, you're only limited to a 6 foot by 6 foot by 3 foot part, which I know only works for a certain amount of people. On here, you're a little bit smaller than that, but all the same welding capabilities. The one big difference on this machine, though, is that the welding device is actually treated as a tool. So just like putting a regular Cat 50 tool into the spindle, we kind of put our welding device into the spindle.
Really? You tool change that out?
Exactly. I mean, it's not exactly going into the tool carousel, but same principles.
How much does the system that comes out, you know how much it weighs?
Around 500 pounds.
Oh, wow.
So
Okay.
it's a pretty heavy tool.
Heavy.
So if you're actually looking at it, it is two Cat 50 holders with two pull studs, which is
Okay,
how
so
we can get
here's
away
your,
with it.
here's your spindle, but there's is that another one right there?
Exactly.
The 50? Okay.
Yeah, so
Okay.
that's our patented gripping and changing technique.
Okay.
So
Can we do a tool change?
we can do a tool change.
Let's do it.
So we will have to close the machine. We will. So. Now you see it in the spindle.
No way. It actually picks it up. Oh, that's really cool. So now it's not on your table, it's out of the way.
Now we're free to do whatever kind of milling or profiling is necessary for the part.
Yeah, and you can do that it's multiple times throughout a part if you needed to.
Exactly. Depending on your geometry, you might change 3 times or you might change 50 times.
Okay.
It's whatever necessary per the exact part.
But it could be a lights out. I mean, it doesn't necessarily need to be attended.
Not necessarily, no.
That's really cool.
So very, very small comparatively to the larger machine.
Yep. Well, that's warm. How is that so warm?
Some materials that we weld, we do weld at a slightly preheated temperature.
Okay. So that's a heat plate as well?
It is a heat plate as well.
It's a vacuum plate, chuck, and a heat plate.
Exactly. It is a very complicated work holding solution, but it's very unique to UAM. Here what we're actually doing is we're actually embedding a fiber or one of those strain sensing fibers into a part. So if we're going to embed a fiber into a part, we can either 3D print the entire thing, or we can start with some amount of that final part and then just add whatever needs to be added to put the sensor where it needs to be. And here we're actually instrumenting a 3-inch aluminum tube with a strain sensing device. So what we're doing is we're just fixturing a 3-inch tube, cutting down to exactly where we want the fiber, which if you look at this...
Okay. So you only print above where you have to insert the fiber.
Exactly. So if you actually look at this, this is a 6 thou channel. that runs through here.
I can touch it?
Yeah, sure.
Oh, look at that.
So if you
No
look
kidding.
at that continuous channel path.
This part actually is really warm. That's interesting.
Yeah, well, it's higher thermal conductivity than the steel.
Interesting. No kidding. So you machine that in there, lay the wire in, and then
Weld directly over top. And just like that, we have a sensor and a part.
amazing. So you machine that channel such that the fiber will just slightly compress in there?
Yeah, essentially the channel's slightly oversized.
It is oversized, okay.
Just a little bit. So it's oversized just a little bit, so it kind of sets in there. And it allows us to get good placement of the fiber.
Okay.
So for this particular project, we're putting the fiber in strategic locations.
Okay.
So it allows us to kind of control that, and then also it allows us to build it into the metal part without damaging it.
Sure.
So it kind of serves two purposes.
Yeah. Is the fiber hollow?
No, it's a glass core, so it's like a pure glass, and then another glass that's on top of that called cladding. So it's kind of opaque. What that does, it helps keep light in the core, and then on top of that is a plastic.
Okay.
For just handling and protection.
Yeah, it doesn't break. Okay.
Yeah, so they're commonly used in communication industry. But for this particular company that we're working with, they use them as strain and temperature sensors.
Yeah, it's amazing.
Yeah.
So what's going to happen to the tape?
So I'm just holding the tape here just to help keep the fiber in there right now. So it's just a way to help me as I get the fiber positioned.
But you're going to have to take the tape off.
Correct.
Okay.
Yeah.
Cool.
Roll the whole thing.
Oh, that's awesome. You're going to test it
Yeah. So
before you put it in there to make sure.
Right. Our quality.
Oh, look at it light up.
Yeah, so we can see that there's red light there at the end.
Yeah, I don't know if it's going to come on camera, but we can confirm you haven't broken the.
Right, so
wow.
that's our quality control. So we make sure that we're getting light that's transmitted, before and after welding. Because if you don't do it right, you can damage the fiber.
Sure.
Yeah.
You really just use super glue?
Yeah.
It's amazing. I love it.
For this particular project, yes. We normally don't.
Okay.
We can get away without it. But this is a little atypical. So this project is we're making a pipe, a smart pipe. So the pipe will be able to measure pressure, temperature, and heat flux.
Wow.
And it's for a NASA. It's for a NASA test facility in Mississippi called the Stennis Space Flight Center. So all they do there is they test rockets.
Cool.
So the piping, how they have it right now is they're measuring these things, but they're using older techniques that are further away from the fuel stream.
Okay.
So they want to measure pressure and all those things like right there, right when it's going into the engine. So that's kind of the motivation for why to do this.
Awesome. That's really sure. That's amazing.
Yeah.
Is that just a powder high temp tape?
Yeah. So it's Kapton tape.
Yep.
Nothing real special.
Yep.
We like to use it because it the adhesive doesn't really leave a residue. It's pretty easy to remove.
Okay.
So from just working with this stuff, it's pretty good. So we still got our red light, which is good.
How often do you break a fiber?
Not very often.
Okay.
Mostly when we're trying out new stuff that we haven't done before. So at this point, Justin's probably explained some of our different tape versus sheet and stuff. So we're going to use sheet here because we can apply a vacuum, and that again helps keep the fiber in the channel.
Okay. Interesting.
Yeah.
That pulls your vacuum? Those thin.
Yeah, that little
Wow, that's
little
cool.
guy.
Yeah, that's awesome.
Cool. So now we can take off the Kapton tape that was originally used to kind of hold it in.
But that's it. We're never going to see that fiber again, one way or the other.
Yeah.
Oh, okay, there we saw it pull in. Yep.
So it just pulls it against it.
Yep.
So another kind of thing that kind of check is just making sure that when I pulled that vacuum on there, that nothing weird happened and the fiber didn't come out. So a good way to look for that is if we see any like wrinkles or high spots that would imply that there's something under there that shouldn't be. And then just also we just use another roller. And just kind of roll along the surface here.
Would you see the fiber if it had popped out?
Yeah.
Okay. That sheet is thin enough to show that.
Yeah.
Wow.
And you know, you can catch it in a time where you don't damage the fiber and you can correct the problem. And so that looks pretty good. So you can kind of see a little bit of a stencil action there. That's just the top of the channel hitting the roller as I go over it. So
yeah, so that is the channel, the path right there.
Yep, there is.
Cool.
The next step is to weld over it. Final inspection just to make sure that I don't have any weird vacuum loops or anything like that. This guy's just going to ride with it.
Got it.
So I'm just going to apply a little bit of tape and fibers. I'm also just going to apply a little bit of tape to the fibers just because there is some cooling air on our stuff. The fibers flap in the wind a little bit. Just a little bit of tape just to help, kind of just hold it down. All right, I think we're ready to run. So this particular part is a little non-traditional. This is a pipe. So like you saw the super glue. So there's some adjustments that we had to make along the way. This is kind of one of the adjustments too. Is normally we don't break up the weld like this. Normally it would just be continuous.
Okay. Oh, you just did left half.
Yeah.
Interesting.
Half. That way I just make sure that everything's still in the channel.
Huh.
So you can see that it's still shining red.
Yeah, sure. The fact that you can even do that is amazing.
So it's just a doing a little bit of a piecewise operation, just trying to hedge our bets a little bit. But everything still looks good. We still have good vacuuming. If we didn't have good vacuuming, we get some wrinkles, which is a defect that just it originates because our vacuum quality isn't very good.
Got it.
But you know, this seems like it's pretty good, so we just keep going.
So you'll overlap a portion of that? That's okay?
It's actually what it's going to do now is it's going to come back over, start over here, and then weld in that direction. So I'm changing the direction of how it's welded.
It's like a push versus a pull?
A little bit. Yeah, so this path, it was kind of a little bit of trial and error. I was running into problems if I just did it in one go. Because sometimes my vacuum quality, I was losing my quality. Whereas this one, it allows us to successfully get her in there. You can see it's still shining red.
Oh, that's great. Yeah.
So that's what we want to see. So
You're happy.
I'm happy, so I can keep laying on more material and finish out the pipe.
Oh, so you have more to build up from there. Awesome. Okay, very cool.
The finished pipe's actually in here.
Oh my
there's
gosh.
2 different layers, and we have a housing here. So what we're going to do is we're going to attach something on here for protection for the fibers. So we'll have like a kind of like an electrical conduit come onto it for
Got it.
protection.
Got it.
So the layer that you just saw was the very first layer.
Yep. So you got a lot more to build up and then surface back down.
Yep.
Oh, that's really cool.
Yep.
So that will be a hybrid. You'll be machining that back. Oh, that's amazing.
Yep.
Very cool.
Yep.
And you're using Fusion to do the
Yeah.
tool pass there? That's
Oh,
awesome.
yeah.
That's so cool.
Yeah. Yeah, Fusion, we really like Fusion.
That's awesome.
Powerful program.
Cool.
Changed our lives, for sure.
Yeah, that's good. We're big fans. Well, thanks again for showing us. I really
Yeah,
appreciate it.
Thanks for coming by.
So we saw Big Blue, really cool. We saw this guy, really cool. And then I literally, I had to laugh. I'm like, wait a minute, what are you doing with that thing?
There's our Tormach.
Can we go look?
Yeah, let's go look at it.
I met Justin because he came and took the Richard King scraping class. And then it's funny to realize he's in Columbus doing this kind of work. And now you guys bought a Tormach and are using it to change the way UAM can happen?
Exactly. So, courtesy of NASA's SBIR program, the Small Business Innovative Research Program, we have funding to develop a 3D printer for the International Space Station.
For the ISS.
For the ISS. So, actually 3D printing replacement parts or necessary pieces while in space.
So this would it would be not for the ISS, like actually in the ISS.
In the ISS.
Potentially.
Exactly. Way down the road.
Yeah.
But
wow.
we're kind of pioneering developing the technology to get there. So it's
Yeah.
kind of an iterative process. If you look at other machines, you get the idea that this might be a little too big for the ISS. So through this program, what we've done is we've actually taken our welding device, which was oscillating at 20 kilohertz, which is a very heavy Mar-aging steel piece. A little too heavy to go on ISS. And
weight's everything.
I mean, our machine out there is over 8,000 pounds, so
Okay.
not exactly feasible. And then what we've done is we've scaled it down significantly to something that weighs only a couple of pounds.
Can I ask you a dumb question?
Sure.
The whole weight savings on something like the International Space Station has more to do with launch and getting it there than it does being on it?
Exactly.
Okay.
Yeah. The cost of launching something into space is tens of thousands of dollars per pound.
Yeah.
So saving several pounds just
Yeah.
in this one tooling is a huge weight savings and cost savings
Got it.
for the American taxpayer at the end of the day. So kind of going from our large machines to the Tormach machine, what we've done is we've downsized everything, we've simplified everything, and we're working to make some parts. And this is hot off the presses. She made her first welds last night, so I hope that she behaves properly for us right now.
Nothing like the deadline of us. I knew you had a Tormach like last month, but we had previously already said we were going to come up, so I had no idea that this was actually part of this story, which is crazy.
It has been a crazy journey, and let's hope.
Does it work?
Let's hope it works.
Wait, so this is still it's still a normal Tormach, right? You can still use
exactly.
it.
This is an off-the-shelf 1100M from Tormach.
Yeah.
So
but you haven't done anything that will stop it from being. It's the same thing. It can be
exactly.
Okay, this is so cool.
What we've done is we've retrofitted it with about 100 pounds of UAM capabilities.
Okay.
And it's actually less than 100 pounds of UAM capabilities.
Got it.
So very small mechanical. Tormach doesn't seem to really care that it's on there. But as we found out recently, it still has the same welding capabilities as our larger machines.
Okay.
The only difference is our feedstock's a lot smaller and our frequency isn't the same.
Got it. Is that literally a Pearson vacuum pump?
That is a Pearson vacuum pump.
That's hilarious.
Yeah, so we really like our vacuum work holding fixtures.
Right.
So this is an aluminum
awesome.
vacuum chuck that we've used.
Yeah, that's awesome.
So
Okay, so this is so cool. So you get your feedstock in here, and that's what you've already run on it.
Mm-hmm.
And then you've got a control box up there for
that is the ultrasonic power supply.
ultrasonic power supply. So
That's what controls the transducers.
Got it. And then literally they're using the USB I/O device to turn on and off the necessary things, the relays, to make
Exactly.
that. Okay, let's see this thing work. Oh my God. That is way. What is this squeaky noise?
So
Like a scrubbing?
30 kilohertz is actually above our audible range.
Okay.
So what you're actually hearing are harmonics of that vibration. So
Harmonics below.
Yes, below that
Okay.
from other oscillating pieces inside of there.
Okay.
So part of the Sonotrode welding device, and the fixturing around it's actually making that sound, or just the loose foils on the plate. They're kind of acting like guitar strings, giving us those other nails on a chalkboard sounds.
Right, so your quintessential, like what, A is 440 hertz, right?
Yeah.
So this is happening at 1,500 times higher, or 150 times higher than that. Something like that.
Sure.
Yeah.
Edit this for whatever's right.
Yeah. No, but you can't come close to hearing.
Oh, no. Nobody
yeah.
can hear this. I mean, even hearing the 20 kilohertz is on the upper range of almost everybody.
Okay.
With the exception of small children, which is why we don't
Which
really
is why
support.
we employ small
No, it's why we don't really support bring your
we
kids to
will
work
not
day.
be editing that section out. Yeah, don't bring your kids here. Okay. That's so cool. Okay, so again, the idea is you can lay down material, switch back to a tool changer. This is even easier because
Exactly.
you're not tool changing that out.
No,
You could be
it just
going back
stays
and
right there.
forth.
The
Wow.
height variation between the two, as long as you don't have a tool in the spindle, you have clearance for the welding.
Got it. Or else you're going to start friction stir welding.
Yes.
Which is a later part of this video.
Exactly.
Okay, that's really cool. Can you show the?
The oscillation?
Yes,
I would love to.
this is really cool.
So this is a fun part of ultrasonics. You can go ahead and
It's
touch
actually
it
a
if
new
you want
update where they finally put in the USBs. We'd gotten decent at finally memorizing the M64P whatever. It's a welcomed upgrade. Oh, it's super weird.
to. It confuses you a little bit. It feels like almost
Feels like it's
hot
running
butter.
away. Yes.
Yeah, it's almost wet in your hand.
It's, oh, you can even hear that like almost like a crystal glass.
A little bit, yeah.
Yeah. That's not hurting it?
No.
Should we expect your
it'll
finger to be wet?
It confuses you a little bit at first. We're just kind of showing it. So this
why
is
is that?
that's it atomizing the fluid as it's touching the oscillating surface.
Gosh, it doesn't even
So
look-
just that's Sonic's on, Sonic's off.
Oh yeah, look at that.
Sonic's on, Sonic's off.
Do it once more. Off. And off. Oh my gosh, it just jumps. What would happen if you put a tenths indicator on that? Wouldn't show anything?
Oh, you would see it.
Yeah.
So our larger machines, the 20 kilohertz Sonotrode is designed to operate about 60 microns peak to peak.
Okay, yeah, that's measurable.
So that's measurable.
Yeah.
This is less than that because it's a higher frequency.
Okay.
It's more in the 30 micron range
Gosh.
at 100%. For aluminums, though, we found that we don't quite need nearly that much scrubbing.
Okay, so there's still a feeds and speeds element to.
Exactly. Just like feeds and speeds with cutting metals, printing metals have just as many, if not more,
Got it.
feeds and speeds and variables to consider. For us, it's really how hard are you pushing down, how fast are you moving,
Yeah.
and what is your oscillation back and forth? How hard are you scrubbing those metals
Got it.
against each other?
So aside from NASA and JPL and the ISS, there's seems to be a potential consumer or business use here for this sort of technology, right? Is that part of what you're thinking?
I hope so. I mean, part of the SBIR program is really allowing small businesses to develop new cutting-edge technologies for consumer use.
Okay.
So it'd be great if this could be in somebody's garage someday,
Yeah.
3D printing metal, making some of the same parts as we're making in some of our large machines.
It reminds me of like Teflon and all the other laser CD players that we got as derivatives of the Apollo program.
Exactly.
Cool.
It's a wonderful combination.
Yep. Sweet.
And
So what's next up for you? This is your baby. You're working.
this is
on,
my baby.
Yeah.
I hope my wife's not watching this. This is my baby right now.
Highly, according to my YouTube statistics, highly unlikely.
Kind of just taking this to the next level. We want to fully automate this system to be able to 3D print lights out
Okay.
for truly mimicking what it would be like to 3D print parts on the International Space Station.
Okay.
And one question I do get on this every time somebody new sees this is there a 3D printed part on this
yeah,
edition?
sure.
So the answer is yes. There
Okay.
definitely is, and it is like a necessary piece of this. We love our heat exchangers, and actually for cooling our Sonotrode and keeping at a consistent temperature,
Yep.
we had to create a heat exchanger for this unit.
Okay.
It's
So
both,
what's the printed part?
so this aluminum panel across the front
Oh,
is
right
entirely yes, that's entirely 3D metal printed.
Wait,
it's kind of a
there was no billet to there?
there is a little bit of billet to it.
Okay, but not the majority is.
Yeah,
cane.
exactly.
And that's what's funny is that's small enough where that could in the future be actually made on.
It
this
would
sort
be
of-
made on this.
That's amazing.
Yeah, so it's kind of a dual purpose. It cools the sonotrode and keeps everything consistent, but it's also a chip guard. So
Got it. So is there an
gotta be
active
functional.
cooling system with a circulating fluid through there?
it is just air.
Okay.
It's an air nozzle in order to get into areas that were really difficult for us to do any other way.
Got it.
It's all very compact, and that's where
Yeah, I can do
UAM and 3D metal printing really lends itself to solving a lot of solutions or solving a lot of problems with really great solutions.
Very cool. Justin, thank you for the tour. This was
It's been a
amazing.
pleasure.
Awesome. Yes. So your name is
Michael Eve.
Michael Eve, and you run or do.
I'm an application engineer in our friction stir welding group
Okay.
and solid state welding.
Okay.
So kind of what my job is to go find unique manufacturing challenges and then come up with solutions to those.
Okay.
And a lot of my technologies, so by solid state it means we actually weld without melting the material.
I don't understand that yet because
Okay.
it seems cool, but how do you weld without the heat and melting?
So you still get very hot.
Okay.
Probably 80% of melting temperature.
Okay.
The whole point is metals want to bond together. Naturally, atoms want to once they get close enough, they want to bond.
Yeah.
So the whole point of solid state welding is to get those materials close enough and at a high enough temperature that they join.
Physically close.
Yes, physically close.
Interesting.
So, one of the first forms of welding was forge welding. We actually just got something hot and then hit it with a hammer.
Sure.
So the same basics behind forge welding, we're just finding new ways to do the same basic science.
Okay.
So,
Yeah, nothing about this looks like welding to me. It looks really cool, but it's not what I think of when I think of welding.
absolutely not. And that's one of the biggest challenges we have, especially with these technologies, is getting people familiar with them.
Okay.
So, when you think of welding, you think of the typical arc deposition where we have a filler metal and whatnot. In most solid state welding techniques, we are not adding material. We are just joining existing material.
So, but I see, that looks like a MIG welder to me, right? You
Yeah,
gotta
that is a
feed-
MIG welder.
Okay.
That is a MIG welder
Okay.
right there. So on this end, it is a MIG welder. Now on this end of our cell, which was designed to actually drive an assault vehicle into and then be able to do both arc repair and friction stir repair.
Okay.
So,
Wow.
yeah.
This actual machine, or this is a prototype for a machine that would exist?
So
out-
this is an actual friction stir welder.
Wow.
This was built by GTC down in Cincinnati. I'm not sure if they're still making friction stir welders, but there's several companies
Yeah.
out there that do make friction stir welders, including like Bond Technologies, ESAB makes some, and there's several other suppliers. But yeah, this was a custom built machine. It's on, so if you look down at the floor here, we have solid steel plates.
It's amazing. It's like the,
for
the
all of our
largest
tooling.
fixture plate I've ever seen.
Yeah,
It's great.
and then we're relatively flat across here within about 10 thou from end to end on these
Wow.
plates. So, and then just due to some of our military contracts, over time we've acquired some pretty specialized modular tooling.
Yeah.
So the whole point of this thing is that we take a third body tool, which I'll go grab one for you.
The machine is amazing. We're standing inside.
So the friction stir tool is the piece of the equipment that actually goes into the material that's going to be welded.
Yep. Okay.
So you have a pin and a shoulder. And essentially what we do is we spin this tool, and as we spin, we generate heat through plastic deformation and a little bit of frictional heating, but mostly plasticizing material.
Okay.
95% of that energy is given off as heat.
Okay.
And then once we plunge it into the material, we start to travel along and
Okay.
make a weld as we're spinning.
Interesting.
Even though we get hot and soften the material, this is a very high loading process. The thicker the material, the more loads that we have, and depending on the material grade as well. This machine is one of the most capable machines in North America.
Wow.
We can go in the Z-axis, so downforce, up to 60,000 pounds of load.
Oh my
Yes.
God.
X and Y up to 15,000 pounds, and about 1,800 foot-pounds of torque. Now, when we actually need those kind of loads, we can do 3 inches thick in aluminum, so 6,000, 7,000, 2,000 series on a single pass. When we're doing that, we're only traveling maybe an inch a minute. But if you compare that to how many passes in an arc weld that would be,
Got it.
and the fact that a friction stir weld, we can get anywhere from 60 to 90 to 100% joint efficiencies, depending on the starting. So how much strength knockdown do we get because of welding?
Okay.
So with an arc weld, you're lucky to get half. Not only are we not having to add material, there's no joint prep besides just two feigned surfaces, just nice and square.
Just together.
Yep, just
Really?
butt them up. You know, some people do this with saw cut edges. I recommend a quick milling pass, like 32 RMS, 16's probably even fine.
There's no ultrasonic in this, there's no heat,
no.
it's just turning.
It's just solely the heat generated from moving this tool
What
in the
sort of
material.
RPMs would that be rotating at?
The RPM range in a friction stir weld is very dependent on the thickness.
Okay.
So if we're very thin, we could be running at 2,500, 3,000 RPM and traveling over 120 inches a minute on very thin materials. We're talking, you know, 30, 40 thou thick material. It's not a linear ramp, but once we get up to, let's say, like a half-inch thick, maybe we're at a few hundred RPM.
Okay.
And then when we get to an inch to a few inches thick, we're in the 160, even 50 RPM range.
Okay.
And that's when our torque values start to really skyrocket.
Sure.
So I mean, it's still total energy input because I mean, it's the same, it's just physics. We have to get it warm in order to lower the yield strength in order to be able to make it flow.
It's interesting because I've heard about some, they're not necessarily new, but new certainly to the smaller guys, about ceramic cutting tools where the only way they work is by plasticizing the material at the cutting edge. So they have to be running incredibly high surface feet per minute to generate that heat to allow that to happen.
Exactly. So a lot of the modeling is all about that surface feet per minute heat generation.
Interesting.
And so as you can kind of see right here, the friction stir tools, there is a wide variety, and this is kind of the black box and a little bit of black magic in friction stir welding. So this is an aluminum tool. So you can see, even though we have a little of aluminum adhered to it, we have threads and flats. So the threads really help push material towards the bottom of the tool.
Okay.
So we actually, you can design it to pull material up towards the shoulder or push it down towards the base of the weld. We find that pushing it down gives us better weld properties. And it really just depends on the chemistry of the aluminum, what's going to be the right tool. So the amount of material that we join, the thickness is determined by the pin length.
Okay.
So, you know, what we're looking at here, it's about a half-inch welding tool. And the kind of purpose, so the pin moves the material. The shoulder's purpose is to help generate a little bit of heat, but mostly keep all this warm material inside of the joint.
Got it.
So that's where all those high Z loads come from, because we have to actually physically compress and keep everything inside the joint. If we get too hot, we'll actually start extruding out material and create flash.
Got it.
So if you want to follow me over here, we can show you some of the joints.
The tools are very much a consumable.
Yes and no. So for thin aluminum, you can run a tool for thousands of feet, and you know, there might only be $50 to $100 once you have them in production. When we get to welding thick section steel, yes, they very much become a consumable and a high cost item.
What are they made of?
Aluminum tools are just made of tool steel, like H13. As we get to some of those thicker sections, we like to use some cobalt-based superalloys that are, they still machine like it's like cobalt nickel iron blend material. They still machine like a tool steel, but just give us a little better high temperature properties. When we get into steel, and this is where EWI really shines, we go to tungsten-based tool materials. So actually put that in your hand. And it's very, very heavy. And that is a few $1,000s an inch.
Wow. And it's,
so, yeah, so Tungsten Rhenium Alloys Incorporated, they're up in Northern Ohio, actually specialize in making the material, and partnering with them, we can actually commercially buy those. So we need tungsten because, like I said, your melting temperature and kind of your yield strength versus temperature curves really matter with this material. So with steel now, we're getting up to 1200 C, 1400 C in order to stir this material. So if we try to use a tool steel, we'd be melting that tool as well. So that's why we get to this tungsten-based tool material where your melting temperature is 3000 C. And you still have quite a bit of high temperature strength in that regime. So there's a wide variety of joints that we can do. So this is thin magnesium.
Okay. Oh my gosh.
Yes. Yeah.
Wow.
So we went right along the joint there and made a solid state friction stir weld.
And there's been nothing else.
There's nothing else done to this.
Grinding or prep or polishing. It's just
that's as welded.
Wow.
That one we had specifically designed for minimal flash. Here's about a 2-inch thick sheet of aluminum that we've welded.
This is mind-blowing. Those are just butted up against each other.
Yeah.
And then stir welded like that.
Yeah, so
Oh
we
my.
plunged in here, and when
Okay.
we do leave an exit hole. I mean, fundamentally, when we retract the tool, there's going to be a hole. We can't, like I said, we're not adding material, we're not creating
Sure.
anything doing this.
Okay.
But
You couldn't come off the part?
yeah, so run-on, run-off tabs are an easy way to get rid of
Okay.
this. For circumferential welds, we can actually retract the pin very slowly and leave the shoulder in contact with specialized tooling
Okay.
to minimize, just leave a very slight indentation. So that's called a retractable pin tool. It was developed by NASA. It's on Spacecraft for like the second stage boosters. They use it to join all of that.
Okay.
So NASA actually developed that RPT
Cool.
technology.
So if we were to just pop that into a machine and deck off the top, you'd have this hole here, but otherwise it would look like a single monolithic piece of,
Yes.
it's amazing. Oh, sorry, don't worry about that.
Oh, well, I don't want to lose your guys' equipment. So,
We'll just trade you.
no. Well, that has minimal resale value. Despite the rhenium being really expensive, there's no good way to recycle it.
It's funny.
So, this is a 1-inch thick titanium weld, Ti64. And this is zircaloy. So, I mean, we have done the gambit of materials here, up to 1-inch thick in copper, up to 1 inch thick in steel.
It's incredible. An inch copper?
Yes.
Oh my.
So the copper is great because friction stir welding leaves you with a very conductive microstructure.
Okay.
So for things like bus bar applications, this is excellent because you can take something that's very close to like commercially pure copper and join it and maybe only get a couple percentages knocked down in conductivity. And for things like land turbine generators, where heat generation is key because they're pumping so many amps through this, it's really an enabling technology to get away from brazing, where you have no quality control methods, and the worst case, even a bad friction stir weld has a lot of structural integrity.
Got it. If you're in the same room when some of these stir welds are happening, is it loud, very violent?
It's actually
process?
kind of boring, to be honest.
Really?
I mean, it's quiet. It's just
It is.
it's running. With the steel, you might see a slight glow, but with the aluminum, if you've seen one, it's actually kind of a boring process.
Interesting.
Yeah, so this is actually steel that we did on a pipe. So you can see there's a nice radius there.
Sorry, is this a 5-axis sort of where you're keeping it normal to
So
the
actually, so it's we have a small version of the rotary table set up right over here.
Okay.
But the machine is fixed, and we're actually using a very large turntable to just feed
Okay.
the part through.
Got it.
So this is a 5-axis machine as well. So
Really?
we have,
It's amazing. It's an amazing
yeah.
machine.
So clearly, X, Y, and Z.
Yep.
But we also have an AB access if you want to come over here. So right now we have a local clamp on here. So
Okay.
this helps provide the downforce needed for welding. But if you get right up in here, you'll see two kind of concentric plates.
Yeah. Okay.
So that's our AB axis. And
Interesting.
so we actually get plus or minus 20 degrees tilt in any direction.
Really?
Yeah, on this machine. So we can do complex 3D shapes, go around curves and whatnot. And when we get into, there are friction stir welding robots, but they have a much smaller load capability.
Yeah, sure.
But for this, we can integrate this with rotary tables and other, unique pieces of fixturing and do, elongated hot dog shapes, stuff like that. We've done it all.
It's a really cool machine design. You've got this, this fixture plate on the floor. You've got two very large rails on each side running along. You call this your X or Y?
So this is our X-axis.
X-axis, and then you've got kind of almost like an inverted bridge where you've got the rail mounted upside down underneath here with your trucks. It's really cool.
And we actually have, there's actually two spindles inside of here.
Okay. Oh, it's
So-
angled right now.
Yeah. So typically we just drive with the main spindle.
Okay.
But when we're doing that RPT welding that I was talking about, we have those-
Retraction?
Yeah, where we have the pin and shoulder separate so they can move up and down to
Okay.
minimize the exit hole. We actually need to drive the pin separately. So there
Cool.
are two different spindles that can
They're
operate.
in line though.
Yeah, they're in
Whoa,
line.
that's
And we
awesome.
can water cool the backside of our tools as well. It's quite an impressive piece of
amazing.
equipment. Oh,
Was just
there's so
going,
many
look at that.
different shapes and sizes.
Sure.
I mean,
So that's before it has had some chip weld. It's funny,
Yeah.
I've
So
actually
that has a
chip welded
different-
myself, but usually not with the intention of stir welding, or
Yeah,
just a
yeah,
bad
exactly.
machining day.
so that has a scroll on it, so that's a different feature on the shoulder.
Okay.
That prevents material from being extruded out the sides.
Yeah, sure.
And it leaves a very nice smooth feature.
Very cool.
So not only is the plunge depth, speed, and feed rate
Mm-hmm.
one of the things, the tilt angle matters as well.
Oh,
So
interesting.
these
Sure.
ones are actually run at a 0 degree, while as the cup shoulder tools, like one here.
Yep.
We actually run that at like 1 to 3 degrees, and we get more forging load on the backside.
Yep.
Doing that.
Makes sense.
So, pretty
It's
cool
like
stuff.
inducing a tram error into the machine as you push across.
Yes,
the page.
exactly, exactly. So this is my colleague, John Seaman.
How's it going?
John is also in our Frictional stir welding group, and he and you could talk to him about the machining and guts of the machine. I'm more of the we're both process guys. I'm more of theory, and John gets into it.
It's a really cool machine. Anytime you can walk into and through the machine, it's a good day.
You can
But-
drive through it, I think.
Yeah, the only other thing that I haven't really talked about is the fixturing requirements.
Sure.
So tooling is key for this process, because I mean, we were just talking about the loads earlier, the down forces, and then up to 15,000 pounds travel, and the very high torsional loads. So physics still apply for this process, so we still have to react all those loads without our pieces moving.
Yep.
So we do that through the use of end stops. So in the direction of welding, we have to have a hard stop. We have side clamping loads, so you can see the jack bolts there. So we squeeze everything together.
Yep.
And then we have top clamping, and we do that through the use of toe clamps or local clamps. So here,
rolling on before.
yeah,
oh,
we
it's
actually have a
beautiful. Love
rolling
it.
and a
That's
hydraulic
awesome.
system that follows the tool in this case.
Sure.
So
You need to keep it pushed down, but there is no force lifting it up.
no,
Right.
it's
Side
solely
and-
reaction.
Yeah.
I mean, it's because we're moving material down. If we don't have good top clamping, you actually see a little material hump extrude out the bottom. But it's all fun things.
That's cool.
So not only can we do butt joints, we can also do things like T-joints and lap welds. So that was actually an integral stiffener. And then we left our fixturing a little open to extrude out a fillet as we were welding.
Right.
So
That's incredible.
yeah. And then, we're doing pretty unique things to the microstructure as we're welding. So we're, we have things called grains. They're typically very big. We end up with very fine grains when we friction stir weld. So this is actually changing the through thickness properties and adding this top plate on while we're welding.
Yep.
So pretty cool stuff.
Yeah, we saw the sample piece out in the hallway that showed that cross section cutaway. That was amazing to see.
Yeah,
how-
so that was like friction stir additive.
Okay.
Additive's a loose term there. It's really friction stir near net shape manufacturing.
Okay.
But kind of my vision for that technology is you have an existing very large preform, and you want to locally add height or feature somewhere. So think of something like, you have like a aerospace body and you want to put a mounting plate locally on. Right now, the only way to do that is to start off with something that's maybe twice as thick as your final component, because then you have to machine all this away and there's chips on the floor.
Yeah.
So to locally be able to add material that's like for mounting brackets or local ribs to stiffen it, I think we can really reduce our buy to fly ratios in the aerospace industry using stuff like that.
Cool.
So any questions? I just kind of rambled for a while, and I know you guys got a lot of stuff to do.
It's definitely stimulating. This is pretty impressive.
The whole idea here was to make a complex part using friction stir weld.
Okay.
So if you want to zoom in here, basically we're only joining material where the tool would pass through. So this is flash, this is just material, it's been extruded out.
Okay.
But essentially this would be building up like one of those rib features that I was talking about, where we're doing repeative welds to build up, half-inch thick layers of material to end up with a solid section.
Each is a pass, so you have multiple passes after you've added.
Yes,
You
yes,
drop a
and-
bar down, go over it. Drop
Yeah,
a bar
so
down.
actually here we did 5 separate welds that you can see because we've etched this. So first weld, second weld, third weld, fourth weld, fifth weld.
Got it.
And then we do a quick fly pass so we had a nice flat surface to do the next weld.
I see.
Plunged in just a little bit, so the tool only goes a little bit into the top sheet,
Interesting.
or through the top sheet into the bottom sheet in order to make the weld. And so by repeatedly doing this, we were able to build up a pretty complex feature. So if you thought about traditional machining, we would have needed to start with a block of material that's almost the entire size of this plate.
Right.
So by starting with just plate material and then using friction stir welding, we're actually able to build it up and end up with this solid cross section that you're seeing here.
Got it.
I mean, this is in its infancy, but it's really just repeated welding, which really any additive process is repeated welding for the most part. So it's just a cool thing that, there's some interest in industry with this right now. It definitely shines in aluminum, but it's just something we've been working on.
Interesting. So you're thinking, potentially avoiding the need to do things like castings or large amounts of material removal for.
So, friction stir is an expensive process.
Okay.
Its cost of running it's not very high, but I mean, you saw that machine out there.
Sure.
And that is an overkill. But depending on your application, your machines can range anywhere from a few $100,000 up to a few million, or several million, depending on the capabilities. So it really has its niche applications.
Got it.
So casting is a very efficient process, and I'm not going to sit here and say that this technology is going to replace castings. Now, where you need something very high strength, like in an aerospace component, using 7000 series, something that doesn't lend itself well to casting, and then in order to forge this geometry, you're still left with quite a bit of machining.
Yep.
This may be a very good option.
Got it.
So,
or for one-offs, you're not going to build the tooling.
oh yeah,
right
exactly,
Okay.
exactly. For one-offs, or maybe you're making 6 parts a year for space exploration things, and then this gives you so much flexibility that you can make 8 different parts using the same setup.
But just so I understand it, this could literally be just brackets of steel that were cut on a press brake or a plasma, making sure they're clean and flat, and then you just lay them in there and friction mold them.
Yeah, so once again, I would stick to softer materials like copper and aluminum, but yes, you could order plate material. We still need to account, so since we're doing lap welds, we really just need to have some sort of stop, and then if you had just modular toe clamps that could come in here and grab, build up.
Let's go.
Or integrate it with some sort of robotic clamping, you can make tons of different shapes.
It doesn't require special aluminum, it's the same aluminum.
No, it's same aluminum. Pretty much anything. The beauty of friction stir welding is because we don't melt, we don't deal with all these solidification issues that you have with most aluminums. So any aluminum that you're going to use for manufacturing, this process can join.
Very cool. Again, thank you.
Hey, thank
Appreciate
you
it.
guys.
Take care. You are Rodrigo.
Yes, with the AM team here in EWI Columbus, we do all of our powderbed fusion here, the laser powderbed fusion,
Okay.
which is a type of additive manufacturing. I know you've seen ultrasonic consolidation, you've seen friction stir welding, additive manufacturing. There's also directed energy deposition, which is what we do on the lasers team.
Okay.
Big robotic stuff, additive manufacturing. Laser powderbed tends to be a little bit smaller, more fine precision features, but still all the nice benefits. You can see some of the parts here.
Yep.
Probably seen around. This is a portion of a rook,
Yep.
the classic part everybody shows. We stopped it halfway through. You can see some of the features in there.
Inside there.
That really lets you see some of that capability. We have 2 machines here in Columbus of laser powderbed. We have the EOS, which is a standard commercial type of machine, in which we do a lot of for commercial work. We also do a lot of bleeding edge hardware development, in which that wasn't working for what we needed to, so we ended up building our own machine from scratch, which is the open architecture machine.
So this is a machine that people use in industry right
Yes.
now. You can print parts of it. Anybody can buy one, operate one, etc.
Yeah.
And this is a roll your own version.
Yeah, this is what we decided to do when we said we're going to develop some surrounding hardware for the equipment.
Okay.
A lot of what we do is monitoring and process control,
Okay.
and that's in-process monitoring. Right now, this is kind of black boxy. You can only get a video, maybe some data. This is to enable people to do more and more new equipment.
If I heard that somebody built their own metal sintering printer, I would say no, that's not possible. That's crazy.
No, but with it, and it's actually pretty fun. Contrary to what that one does, that one controls itself vectorially. It's a digital file. This one runs on Aerotech 3200 G-code.
Okay.
Straight out G-code, like the one you see on CNC machining. If I open the screen, you would be familiar with G1s, G0s,
Yeah.
G2s, dwells.
That's controlling the laser, though?
Yeah, so it controls the axis of the laser.
So it controls where the laser's aimed.
Yeah,
Interesting.
and it also controls the recoating arm, the dispensing of the powder, the build plate, which moves down,
Yep.
as well as any other sensor we want to plug in it.
Got it.
So a
So
lot
when
of
you say
things.
you built this, you literally built this.
Yeah, from scratch. I mean, the team built it from scratch, but yeah.
Sure, right. Oh my gosh.
But yeah, it's from scratch.
You would not do that to save money.
No, you wouldn't do it to save money. It's a very expensive machine. We did it because we had clients. So there's 3 main works that we do.
Yeah.
Process development,
Yep.
material development, and hardware development.
Okay.
Hardware development was hard to do on a
closed
commercial
system.
system, it's nice, it's reliable, but they're closed.
Sure.
And we needed a lot of signal data that they weren't giving us.
Got it.
So we just replicated the process over here.
Wow.
For a certain type of client.
Yes. Because you don't print as a service. You're doing it for testing and
we build some parts. You see some of the parts over there, but a lot of the parts we end up building are development samples. We have a comprehensive material development process, and it culminates when we build complete walls that then go to machining and testing or whatever the client needs to do with them to verify that the process is up to spec. These are some sample parts, corrosion testing samples, and walls for machining.
One of the things we've seen when you go to actually run one of these machines is because you're working in a three-dimensional cube, you end up nesting as many parts as you absolutely can into it. So then you pull it out, and in this case, it looks like you've got to run is it a wire EDM to break the parts off?
A saw. You can do a wire EDM, but sometimes this is a porous structure right here. So the wire doesn't like the engagement, disengagement.
Interesting, okay.
If you had a solid piece, yeah, for sure.
But nevertheless, you've got another step left to get rid of this material off the build plate.
Yeah, and unlike, you've probably seen the plastic sintering machines, which you can 3D nest.
Yes,
truly 3D
that's what it would be, only for plastic.
Metal 3D printing doesn't do 3D nesting.
Okay.
Because you have to basically weld your part to the substrate and prevent it from bending.
To clarify, the three-dimensional nesting is only for the plastic process where you've got usually a dissolvable or soluble support material. Here, you've got to have everything secured down. So you can do things like this though, which is going up off. These are all connected right now.
Yeah, these are welded.
Did you print the base as well?
No, we machine the plate.
You machine that.
And we make it thick to prevent the part from basically potato shipping on themselves. Sometimes the force are strong enough to strip the screws, if the part is big enough, I've seen screws get stuck on the roof of the machine from just the force.
Oh my god.
It's significant.
That's incredible.
You can see the machine right now. We're doing some simple shapes just to show it. Nothing proprietary or otherwise. There's 3 pistons in here. There's the center piston, which is where we're building the part, where the substrate is. That goes down 40 microns, 20 microns, 60 microns, whatever the layer thickness. The right piston contains all of our powder, and that goes up a multiple of that layer thickness to give enough powder, and the collector just gets all the leftover powder.
Got it. Which can be recycled into the right side?
Can be recycled, there's some caveats to that. It can be recycled. The recoating arm will move back and forth, spreading the powder, and you're seeing the laser just basically scan. And we can see every layer that's happening. We can see them over here. Let me just open the profile.
So we'll see if we get it, but it's basically going to use a laser that's on a
on a galvo system.
Thank
Two
you.
mirrors.
A galvo system, incredibly fast. And then once it's done with a layer, we'll see an arm move across. It's probably going to be a while if it's got more work to do.
It's going to take probably 2 more minutes.
Oh, okay, sometime.
The laser's moving at roughly about 1,000 millimeters per second. A meter per second.
Wow, per second.
It looks a lot slower because it's moving and turning around.
It's not, the laser's a single, it's not a line, it's an actual.
It's a point.
It's a point. So that what looks like a line there is actually the laser moving. Oh my god.
It's an 80 micron spot, so 0.08 diameter on that spot. The weld that is making, because this is basically just micro welding upon micro welding.
Sure.
The weld is about 120 microns.
The weld is 120 microns.
The melt pool is roughly about 120 microns.
So this is metal, just like an extrusion. Well, not like an extrusion, but
this is maraging steel.
Yes, right.
And we can also do Inconels, titaniums, aluminums, stainless steels, Hastelloys. We develop parameters for clients.
So that pulled off the old material.
Doesn't pull the old material, just goes and retrieves new.
Retrieves new.
And then spreads it out.
And there we go.
And repeats. And we can see every single layer that it's making. That's what the layer that it's currently making.
Okay.
And you can see every layer that came before it. And you can see every layer that's going to come after.
Coming. Oh, wow. How often would a machine like this have a print fail?
By the machine, not that often.
Okay.
Because you set up the file incorrectly if you're doing a complex geometry. These are just simple geometry, so it might not fail. That happens more often.
Okay.
by mis-setting, but it's the equivalent of setting up the tools and tool paths.
Yeah.
You can mitigate that by experience and by understanding when you put the supports, where you put the supports, how much supports. That tends to mitigate, so long as you have a correct recipe, the speed and power and distance of the parameters.
Because as the build plate lowers, because it's continuously supported by unsintered powder, you can have unlimited overhangs?
Not unlimited. That does happen on the plastic sintering machines. On this one, no. To an extent, which tends to be the 45 degree, then you stop. Then you start supporting.
It does, okay.
You need to support because of the heat sink happening onto it. And the powder, unlike on the sintering machines, this is full melting. Doesn't have any strength to support anything.
Just push away.
This is floating.
Got it.
Free floating. And the chamber is full of argon, so it doesn't oxidize while it's going on.
Holy cow. So every time it consumes argon every time you set up a print to pressure. Wow.
It doesn't, some machines consume more than others.
Yeah.
It will give me about 200 hours on a single tank.
Wow. It's really cool.
And then the parts, depends on what you're doing. If you're doing near net shape manufacturing, you can take the parts and machine them, which is an interesting step. Or you can take the parts, polish them, you can heat treat them, hip them.
What material did you say this is?
Maraging steel.
Okay. And does it come out in what would be considered an annealed state? Are there stresses in it?
There's a lot of internal stress.
Okay, there are.
Because it's basically welding. So imagine the strains on a weld, now multiplied by 1,000,000 on every single weld line.
Interesting.
Because that's what every laser pass is. It's a weld line.
Okay, but there's no normalization that occurs through...
Not here. You have to normalize it.
You do.
And you normalize them normally on the plate.
Oh, before you cut them off?
Because if you cut them off, they'll potato chip on you. They literally potato chip.
That's amazing. Oh my God.
You have, I think, an FDM printer, a smaller desktop printer.
Yeah, we have a
those potato chip on you. Those peel off from the plate.
Oh, really?
Our lower end one does. The Mark IV does pretty well.
Because they're heated chambers, but they tend to
It
peel.
doesn't have a heated chamber, actually.
Oh, you have the old model.
And a cold bed.
Okay, so you have the older model. But if you take them off the ABS parts, try to warp. Same warping, just like multiplied by 1,000 because it's metal.
Right. So this is the same thing.
This is the exact same machine.
Did it work on the sort of proverbial first build?
No way.
That makes me feel
no way, no hell.
I love it. It's just like a solid
door,
aluminum door.
So I can't show you the laser because it's off.
Okay.
But we control those unintuitively with the A and B axis. Just feature of the design. In this case, the X is the recoater.
Okay.
The Y axis is the dispenser, or the right side piston, and the C axis is our piston.
It looks like one of those Bell Everman stages on the back side that's just mounted on the...
Yeah, it's a servo with a lead screw and a linear rail.
Yeah, it's almost, simple. Really.
It's simple.
Yeah.
It's a very simple machine when you break it down to parts.
And where is the laser's through the lens right there?
Yeah, the laser is the galvo is upstairs, the laser is on the rack that we have on the side. The source is here.
Sorry, say that again?
The source of the laser
I see.
is right here. The galvo system is up here. And we have different from here, where it's very compact.
That's awesome.
Or semi-compact.
Yeah.
The system, our platform is a lot more open because we have put a lot of other hardware in between the laser and the galvo.
Yeah, no, sure. It's separate world, but in the machine tool world, there's been a huge push now to do lots of vibration sensor, heat sensors analysis for both reactive and preventative maintenance to understand what's happening in your spindle, what's happening in your truck, which is really cool to see.
Yeah, so similar thing, we're doing infrared imaging, profilometry imaging, photodiode imaging.
Cool.
What else are we doing? Some people in Louisville did acoustic sensing of it. They were trying, on other machines, they tried to understand how the machine is vibrating and sounds.
Yeah.
Like how far they can get it, and they were able to reverse engineer parts based on sound from the movement of the machine. So a lot of that work.
Like a signature of, oh my gosh.
Correct.
That's cool.
And I don't know if it happens to you, but you can hear when the machine is working correctly. It happens to you with CNC machines.
Sure.
You can hear it I know it's
You
a
can
lot
hear
more,
it when it
it's-
doesn't work correctly.
Yeah, shatter or other stuff.
Sure.
Same thing here. Right now it's working pretty well. But if you're developing a new material, you will hear the scraping of the recoater as it goes along, and you was like crack, 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 crack,
Really?
and it sounds. Or it's burning too much, and you hear the weld
Yeah.
like bubble a little bit. So you can hear all of that stuff on the
Interesting.
machine.
Very cool. This is amazing, though.
If you imagine, in comparison, you have a line per movement on CNC.
Yes.
Here we have roughly the same
A line per point. though.
per movement of the laser.
Okay. Sure.
Roughly, a little bit more.
Okay.
But imagine that every weld has to be a line of code.
Yes. There are millions of lines of code that
Yeah,
you
so
program.
some of our files have roughly 100,000, and this machine smaller files, 100,000 lines of code.
Wow.
And these are builds that are an inch by an inch by an
Yeah.
inch.
What do you program I think slicer or
Some of
cam?
it by hand. We have also, when we get to more complex geometries, we build a slicer,
Okay.
for like a complicated slicer,
Got it.
but it's limited.
Wow. Very cool.
And the code looks a lot like what you see. It's just G code, but it allows you to have actual logic. It's a cool thing about Aerotech. It allows you to have actual logic built in it, so you can do loops. If you're having a very big code, you can just loop it out.
Sure. It's just funny. It's on like an 80-20 base. It's
Yeah. This one requires a lot more babysitting than that one.
Got it. What would build time be for
A build like this takes about 200 hours.
200 hours?
Yeah,
Oh
something
my
like
gosh.
this, 200 hours.
Wow.
And the interesting thing is that whether I'm building a single wall or I'm building all the walls,
same.
I have to, no, not the same, but I have to get all the powder for that height.
Right. You can't section off an area, huh?
Yeah, you
Wow.
can't do that on the machines.
Interesting.
So you got to be efficient about it.
Wow. Oh. Cool. I wanted to.
These are some of the other
B-roll,
parts.
yeah.
Some cool ones. This little ball.
Oh, inside.
It's like 10 balls inside there, all built at the same time.
Yeah. Yeah. Wow. Fabergé got nothing on you.
A titanium ball. It bounces.
It doesn't break.
It doesn't break.
Seriously?
Oh, you can stand on it. You can stand on it.
I feel.
I dare you to stand
actually
on it.
feel guilty about doing this.
Do it. I invite you
gotta
to stand
film.
on it.
It's titanium.
Mm-hmm.
I'm gonna fall, you know. Oh my God, that's amazing.
It's pretty strong. It's plenty strong. Roughly, the strength depends on the material, but it
doesn't weigh
oscillates
anything.
about. It's nothing on it. It's hollow. The strength from cast or wrought
Yeah.
titanium, this one is about 75%, and
Okay.
that tends to be the strength for the alloys, roughly there.
Are you seeing any generative design stuff come into your world?
Yeah, Autodesk. There you go.
Are you
also-
using it?
We are not using it because we don't do design of parts too often.
Okay. got it.
Normally the client comes to us with a part pre-designed.
Got it.
We advise them sometimes, and I have used it before.
Yeah.
In a previous life, I used some of the tools before. There's also Altair. There's also
Yeah.
who else? Altair, Autodesk, and there was a third company that does generative.
Mm-hmm.
That's starting to do generative design.
The cubes are beautiful.
This was one of our first prints on the open architecture system.
Oh yeah.
One of the very first.
Is anything else here done on that machine?
Yeah, this one was done on that machine. That one was done on that machine. And I actually just sent out a couple of other parts that were done on that machine.
When you started the DIY build, did you think there was a chance it ended up not working and
No,
being
we
scrapped?
were gonna make it work.
Okay.
We were gonna make it work. There are harder things than making one of those machines.
Oh really?
There's actually for SLS machines, for plastic printers of the same kind, there's a YouTube channel that was building one
Okay.
for a long time. DIY SLS.
You got to be careful with those YouTube guys though.
Yeah, I know, right? They're all crazy guys.
Yeah.
All crazy guys.
That's awesome. We were joking at lunch because there have been a couple people I think who've tried to do DIY EDM machines and no one seems to be able to crack the power supply.
Yeah, the power supply is the hardest one.
Yeah.
And there's another technology called electron beam,
Okay.
which is powderbed fusion. which is it's just an electron beam like the old CCTVs,
Okay.
but on steroids.
Yeah.
Controlling the power supply to get the electron beam correctly,
the focal length.
it's a whole different world.
Interesting. Well, thank you very much for showing us the lab, man. It's really good to
No,
meet you.
pleasure meeting
Very
you.
cool.